Ravi, and I am, as Nikhil said, I am a reservoir geologist. I work for Illinois State Geological Survey. I've been with this company from 2014. Before that, I was a well site geologist. About 5 years, I was well site geologist, and I work on offshore rigs in Persian Gulf. Before that, I was sedimentologist, and I worked for private oil company in Iran. And on that time, I studied the sediments intervals as a sedimentologist to find out sequences, diagenetic trends, also the porosity, permeability, and creating the maps, 2D maps. But right now, I am with Illinois Geological Survey. We mostly concentrate on CO2 sequestration for reducing the CO2 and injecting them into the deep formation. But the concept of these with this work with my past experience is the same, because as a geologist, we must create a model, a 3D reservoir model with reservoir modeling softwares, same as Petrol, same as RMS. So the concepts are the same. Now let's start this presentation. Okay, for creating a 3D model, we must actually integrate several subjects. For example, as a geologist, as a reservoir modeler, we must combine these subjects. For example, if you look at this one at the left side, that's a conceptual model of a basin or maybe a field. We must know what's the conceptual model of a basin. After that, we must know the type of depositional system. What is the difference, for example, what is the differences between the channel system with floodplain? What is the difference of the channel with, for example, deep marine depositional system? Actually, we should use another subject, for example, seismic data. Why we need the seismic data? We need the seismic data to actually the output of the seismic data, the surface seismic data is the surfaces. We must import those surfaces into the software to create the 2D or 3D maps. We also need the data from the petrophysics, for example, the logs. We need the gamma ray for correlation. We need the PE log to find out the lithology. We need the resistivity to find out the type of fluids between pores. We need the neutron porosity. We need the density porosity to find out the porosity. And we need the some pressure data, for example, RFD to find out the oil water contact of the reservoir. So after that, we find out those, After we importing those data into a 3D model, we can create a property model and distribute the property between cells to find out, for example, in the oil companies, we can find, at first we can find out the volume of the reservoir. After that, we can calculate the initial oil in place, recoverable oil from that reservoir. So in the past, if you look at the past papers from, for example, 1940, 1950, you can see most of them use the 2D maps. For example, they estimate the initial oil in place just by 2D maps. They have porosity maps. They have, if they have porosity map, if they have the area of the field, after that they can predict or estimate the initial oil in place. But why our preference is 3D instead of 2D? Because in the 3D model, we can see the special relationship between data. We can find out the heterogeneity of the reservoir. We can better model the faults, especially the complex structures, complex faults that have intersect with each other. And with stochastic algorithms, we can distribute the properties. And after that, we can pass this model to a reservoir engineers for simulation or having a better history match. Okay, so if you look at this formula, this equation, you can see that's the equation for calculating the stock tank oil in place. That's one of our targets. We wanted to calculate the area of the fields. We wanted to calculate the H. It means the thickness of reservoir. Let me just change it to pen. For example, if you have a reservoir, if you have anticline, and this is the oil-water contact, and in the 2D view, you have an oil field with different well location. So you have the area, right? And you have the thickness of the reservoir or the closure of the reservoir. So you have A, that means area of the reservoir. You have the reservoir thickness. Based on log, you can calculate the porosity. Based on log, you can calculate, or petrophysicists can calculate the water saturation. You can get the BO, that's formation volume factor, from reservoir engineer, and after that calculate the initial oil in place. So you can do that with 2D map, but if you wanted to have a precise model and you estimate the initial oil in place with lower uncertainty, it's better to actually go with 3D model. Okay, let's start from depositional environment. Why depositional environment is important for us? Look at these two pictures. The first one at the left is the depositional environment for carbonates. And the second one, I don't know, my cursor is here. Let me change it to laser. Okay. This one shows the depositional, different type of depositional environment for carbonates. You can see, for example, in this image, you can see here is, that's a sea level. We have a deep marine sediments. Actually, that's very important. At first, let me say that this is important for us to find out the trend of sediments or the trend of porosity. For example, that's a deep marine environment. In this deep marine environment, because we have shales, so the porosity, the connected porosity is low. But in this area, that's a beach. In this area, we have high porosity because that's a shore face. The energy of the environment is high, but behind this beach, we have lagoon. So this area actually, in this area, we have very fine grained sediments. So the porosity is very low. So if we have 3 wells in this area, for example, 1 well in this area, 1 well in this area, and 1 well in this area. So in this area, you will find out the sediments with low porosity. In this area, you can penetrate the sediments or interval with high porosity. But in this area, at the upper part, for example, we have a well in this area. At first, you have the lagoonal sediments with low porosity, but we have below that, in those intervals, we have intervals with high porosity. Look at this image at the lower part. We have so many reefs here. We have in this reef area, because they located in the high energy environment, we have high porosity. In this area, we have low porosity. Maybe in this area, if we have a dry environment on that area, we expect to see anhydrite. So the anhydrite has very, very low porosity. And in this area, we have high porosity. But look at this depositional environment, that's turbidite environment. You can see a shelf here. So the slope is very high. We have channel system here, but because of we have channel system here, we have debris flow in this area. So in this area, we expect to have a combination of low porosity interval with high porosity interval. Compared to this depositional environment, we have in the deep marine, we don't have any intervals with high porosity, but in this area, in this depositional environment, we can see deposits with high porosity. So that's the importance of the depositional environment. So at first, the sedimentologists give you, as a geomodeler, give you some maps. So at first, you must create a trend map based on this conceptual model. For example, you can say that in this area, if you have for example, let me change it again to pen. You can with this depositional environment, you can say that in this area of the basin, we have mostly I have the lagunal facies. In this area, we have the barrier system deposits, and in this area, we have the deep marine sediments, and it helps you to better distribute the properties, distribute the porosity, distribute the permeability. Okay, let's look at this figure. You can see very high mountains. In this area, you can see a channel system in this area. This is a meander river. You can see a delta system deposit in this area, and you can see a fan delta in this area. What is the fan delta? If you have a mountain here near a sea level, near an ocean, near a sea, because of the gravity system, you should expect to have a deposit with sometimes with high porosity, sometimes with low porosity, because they are poorly sorted sediments. They just fall off, they wash out from this mountain to the sea. But the size of grains are higher than this delta system in this area. So you should expect to have those deposits in a fan delta. But in this delta, you should expect to have sediments with high porosity in this area, because the high energy environment in this area, medium energy environment in this area, you can see in, for example, seismic attributes, you can see clinoforms, and in pro delta, you should expect, because the energy of the environment is low here, you should expect to see very fine grained sediments here, and with low porosity. Look at this fluvial environment. You can see the alluvial fan in this area. You can see the channel system, braided river in this area. You can see the meander system in this area, and delta. If we look at the sediments from this part to this deep marine depositional environment, we should expect to see larger grain size sediments in this area, medium grain sizes in this area, and fine grain sediment in this area. Also, we should expect to see quartz arenite lithology in this area, because of the high energy system and the feldspars that reworked in this area. So in this area, we have a combination of quartz and also feldspar. In this area, we should expect to see quartz arenite, but in this area, we expect to see very fine grained sediments, same as shale, same as mudstone, clay stone, also sandstone, very fine grained sandstone in this area. So the positional environment is very important for us, because they show us the trend of the sediments. The trend of sediments is important because we wanted, as a reservoir geomodeler, we wanted to model the porosity. We wanted to model the permeability. And these characteristic of the sediment depends to the positional environment and plus the diagenetic processes. So I will show you in next slide why what's the diagenetic processes and the type of those processes. But after that, we wanted to have a zonation. We wanted to divide the reservoir intervals into, for example, several intervals as a flow unit to find out which part has a high porosity and which part has a low porosity. For the zonation, we use the logs, petrophysical logs. But uh, what is important for us is to find not just zonation, not just connect those zones with high porosity to each other. The important part is finding the trend, finding the packages that are deposited in a very similar timeline. Look at this part. For example, this channel system, we have this channel system here, and we have floodplain in this area. Sometimes we have a well, for example, in this part, and a well in this part, because we don't have the deposit of channel system in this part, we don't actually connect them into this channel system. But at the reality, they deposited in a similar time zone. So we should actually find out this time zone. So look at this one, look at these two images. In the past, most of people use this type of correlation. That's just based on lithology. For example, if we actually interpret that this part is sandstone, and in this part is sandstone. Also, we see the sandstone in these wells, also in these wells. So in the past, the geologists just connect those sands together. But after that, with sequence stratigraphy, that was a revolution for geologists. One of the biggest revolution for geology was sequence stratigraphy. At SLOS in Illinois, the first person that find out the sequences was SLOS. SLOS in 1963 find the sequences, and he find out 6 sequences in the Illinois basin deposits. After that, about 15, 20 years after that, Vail and Meacham find out the sequences based on seismic data, seismic attributes. And right now, most of the geologists use those sequences. I will show you in the next slide what is the sequence stratigraphy, why we use the sequence stratigraphy. And you can see that they didn't actually just connect those sediments, those sandstone to each other. For example, we have the sandstone here, but based on lithology, it is not connected to this one. But after finding the sequences, you can connect this sandstone to this sandstone, because they have different characteristics, but actually the time zones are the same. So they can create packages or flow units that are connected to each other. Let me explain it more. Okay. Imagine that we have a field with three, or basin with three wells. And we have a sandstone here. We have a sandstone here and shale here. And also we have a shale, just shale here. If we wanted to just based on that's shale, that's sandstone, and this is sandstone, and it's just shale. So based on lithology, we must connect those to each other. And shale to each other. But actually in the reality, for example, I showed you some of the conceptual models. On those, for example, we have a channel system here, but if we go to deep marine, we have shale here. So we must connect those sandstone to shale, not just sandstone to sandstone, sandstone to shale, because the trend is similar to this. In a similar time zone, in some part we have channel system, we have river. In some part we have delta system, we have deep marine system, so we have shale. So the sequence stratigraphy is a branch of geology that subdivided the sedimentary packages based on unconformity or correlative conformity. What does it mean? For example, if you look at this one, this is a shelf, and we have a sea level here. Okay. So in this part, we have, for example, river, but in this part, we have deposition of shales. So we have a package here, that's sandstone, and also we have shale, but the lower part, because we have channel system, we have unconformity, but here we have correlative conformity. So the packages between this one, and if imagine that in a other time we have, again, we have channel system, and also we have deposition of sediments, we have erosion here, we have also correlative conformity here. So the packages between them create sequences. So they are based on those packages, based on finding those packages, we can have a better zonation to actually divide the sediments and finding the trends. Actually, sequence stratigraphy help us more, because imagine that based on lithology, we just correlate the logs based on lithology. We have sandstone here, for example, 20% porosity here, 20% porosity here, 20% porosity here. It doesn't help us because we don't have any trend. All the part is 20%. But if we look at this part, this package, we have channel system, 20% porosity. In this area, we have about 15% porosity. In this area, we have 2% porosity. So it gives us a better trend, right? It gives us better trend. We have a trend of lower porosity toward this area. For example, if we have a field, we have 20% here, we have 15% here, and we have 2% here. So it gives us a better trend. We can map the porosity based on that, but we don't have a good map for this one. Okay, so after that, how we can find out these sequences? One of the things that help us is finding the stacking pattern. The stacking pattern of the sequences. At first, look at this one. This is the base of the bottom of the sea, and that's the sea level. The distance of this sea level from the base is accommodation. Sometimes the sea level goes up, so we have more accommodation. Sometimes the sea level goes down, so we have lower accommodation. Okay, if you look at this one, for example, if the sea level goes up, the sediments, and we have influx, we have a very low influx of sediments here. So the layer, actually, it deposited the sediments toward the shore face. So we expect that, for example, look at this, at first sea level is here, we have the deposition of the sediments. After that, sea level goes here. So that's the accommodation of us right now. We have again sediments. After that, sea level goes up very fast, goes up very fast. So actually this trend gives us, we can see this trend in the seismic attribute. Look at this one. Look at this one. For example, we have sea level in this part, so you can see that we have the position of sediment in this part. Sea level goes up, and you can see that that's a trend. That's the accommodation is filling, goes up, go up, up. So we have in the seismic system, we can see them. So and we can find actually the attribute of those. If we have this trend of stacking pattern, we call it transgressive stacking pattern. So, and it creates unlap system. If we have some layers similar to this, goes up toward the shore face, we call this unlap. So imagine that right now, imagine that the sea level is here in at the time A is here, but after that, the sea level goes down. Okay. At first, we have the deposition in this area, but after that, we have deposition in this area. Sea level goes down, goes down, goes down, and we can see this attribute in seismics. So they call it progradational. But if the sea level stay in one level, for example, here, and sediment influx is the rate of sediment influx is similar to the rising of sea level, we have a stacking of the sediment onto each other, same as this one. They call it aggregational stacking pattern. Why this stacking pattern important for us? Because actually it shows us what is the type of system tract, what is the type of and how many sequences we have, and we can find timelines and also the boundary of the sequences. Okay, So sometimes, as a geomodeler, sometimes you heard that this type of zonation is layer cake zonation. What does it mean? It means that this zonation is based on just the lithology. For example, we have sandstone here, sandstone here, sandstone here. We just connect those. We have shale here, shale here, shale here. We just connect those. But in the reality, we have it? No. It just gives you an estimate of a very rough estimate of the type of lithology, type of trend of the lithology. But actually, the uncertainty is very high. But look at that cross section that created based on sequence stratigraphy. You can see that we have just loops of shales. We have some loops of, for example, sandstone. In the reality, most of the time we can see it. So if we use the zonation based on this, the sequence stratigraphy, finally, you can see this type of zonation. For example, that's the cross section of the lithology. So you can see this type of zonation. Okay, and let's look at this two other picture. You can, with sequence stratigraphy, you can find better flow units. If instead of this, if we use the lithology-based correlation, you just connect this one to this one and to this one. So actually, you overestimate the property. For example, if you connect this one to this one, and after that, based on this lithology, distribute the property, for example, porosity, so you overestimate. And if you have shale, for example, here, imagine that we don't have this well in this side. You just actually extrapolate this shale interval. After that, what happened? You underestimate the porosity because you extend the shale. So the result, the cross section of the result will be something look like this, because it shows better the sequences. Okay, let's go to Diogenesis. What is the Diogenesis? We say that the physical and chemical changes that affected the sediments after the deposition. For example, dissolution, compaction, cementation, dolomitization, bioturbation. They are the type of the Diogenesis. Why the Diogenesis are important for us? Because they show us the trend of the porosity, permeability. We have different type of porosity in the carbonate, also in the sandstone. Most of the time, we have intergranular porosity in sandstone, but in carbonate we have different type of porosity. For example, intraparticle, interparticle, moldic porosity, fenestrate, shelter, or maybe in both we have fracture porosity. But for example, moldic porosity, fenestrate porosity, intercrystalline porosity is just for dolomite and calcite or limestone. So right now I wanted to show some type of, for example, cementation. That's one of the type of cementation. Is it's in carbonate. That's an oid grainstone. So you can see cement between the grains that fill the pores between the uh, grains. So because of this cementation, we have low porosity. And look at this sandstone. There are, I think there are quartz grains, but we have calcite cement between the grains, so we don't have any porosity here. And that's two type of um, porosity. One of them is this one is for uh, calcite or dolomite. I think that's dolomite because we can see the rhombs of dolomites here. Look at this one, and this is intercrystalline porosity. So we know that if we have a dolomite or dolomitization, because most of the dolomite are secondary dolomite. So after converting calcite to dolomite, we have a reduction, about 13% reduction in volume. Because of that, those volume create pores. But we shouldn't expect to see porosity in all of the dolomite because of the dolomitization. We shouldn't expect to see that. Actually, why? Because of the compaction, because of the overburden pressure of the other formation. We shouldn't expect. But in most of the dolomite, we see porosity. We see this type of porosity. And this is actually sandstone with intergranular porosity. I think we have a question. Okay. Okay, no question. So, okay, look at this one. This is a dolomite, very fine grained dolomite with intercrystalline porosity. I couldn't see my cursor. Okay. Okay, if you look at this image in the left side, you can see this blue one are the porosity between the dolomite rhombs. So we have intercrystalline porosity, and we have, I think we have very large grain of the carbonates, alluvium, or grain of the carbonates here, and after that they dissolve. So we have also moldic porosity. So this actually moldic porosity, they connected those intercrystalline porosity. So we have a high porosity here. Also, look at this one. We have intragranular granular porosity for this carbonate. We have moldic porosity, and also we have some type of vugs in this part, and we have a very high porosity for this grainstone. But you know that because of porosity, and look at these two alluvium, because of the compaction, you can see the between grains we have a solution seams, and because of the compaction we have autogenetic minerals that precipitated in other pores and fill the pores and reduce the porosity. And this stylolite actually created by compaction, so it reduces the porosity. Okay, why this type of porosity, type of diagenetic processes are important for us? Because actually they show us the characteristic of the interval. After that, we can map them, we can find a trend of the diagenetic processes, in which part we have dolomitization, in which part we have vagi porosity, in which part we have compaction. So it gives us a better perspective for the trend of the porosity, trend of the permeability. Okay, let's start the type of maps. After that, when we have the conceptual model, diagenetic processes, and also the trend of porosity for based on the conceptual model. Right now, we wanted to uh, uh, we wanted to actually find out what map we needed to create a 3D model. At first, we need the structure maps. Also, we need the thickness map. For example, isopac map, isocore map. We need some type of porosity and permeability map, deep azimuth and deep angle map, and trend maps. So let's start with a structural map. What is the structural map? The structure map is a subsurface map that shows us the elevation of the formation. For example, you wanted to create a structure map for one formation. You look at the logs, you look at top of the logs based on, for example, gamma ray, based on density logs, based on resistivity log. You will find the elevation of the formations. So you can pick those, and after that, for, if you have so many data, you can create a structural map based on those elevation. And those elevation are based on TVD subsea, not based on measured depth, not based on TVD, they are based on TVD subsea. Also in the structure map, you should expect to see some type of faults. For example, based on regional study, based on outcrop study, the geologists find the uh, trend of the faults after that, or based on the logs also. If the wells have intersect with the fault surfaces, you can find the faults um, between the wells and put them into the structured maps. Okay, right now I wanted to actually explain some of the depths that we imported into the Petroleum or reservoir modeling software. If you look at this well, it's a starting point from here, and it deviated to this interval. Actually, this depth shows the measured depth. That's the realer depth. So, but actually, this is not exactly the depth of the formation. The depth of that's the true vertical. TVD is the true vertical depth from the Kelly bushing, from the starting point to that interval in a vertical direction. But we use the TVD subsea because we wanted to eliminate this part. If you look at this is the sea level. The elevation of the Kelly bushing from the sea level, we call it KV. So if we subtract this depth from TVD, you will reach to TVD subsea. So we don't want actually to put this depth into the software because that's just the elevation. That's not the real, exact real. We wanted to have a reference. If we use this one as a reference, for example, TVD, it's not a good reference to calculate, to correlate the depth with this well because it's higher than this well is higher than it has a higher elevation than this one. So we subtract the elevation to have the TVD subsea, and after that we actually we calculate the depth, or we create a structure map. So this structure map is based on TVD subsea. That's important for us. Another, for thickness map, we have two type of thickness map. We have isochore map, we have isopack map. What's the differences? If you look at this one, that's a TVD. That's a TVD of the total true vertical depth of the well. But from if we actually look at this line, this thickness, this vertical thickness, if we map this vertical thickness, because we have this one, we have the measured depth. Also, when we have a directional well, if we have a directional well, for example, if Schellenberger get the log, the Schellenberger give you a survey file. It shows the inclination and azimuth in different part of the well. So you have the measured depth of this interval, but after that, based on that survey, you calculate, or software calculate, the total true vertical thickness of this interval. But what the reality is isopack. The isopack is true stratigraphic thickness. Look at the isochore and isopack. The thickness of measured depth is higher than the thickness of true vertical thickness. If we have a vertical well, they are very similar, but if we have a deviated well, the thickness of MD or measured depth is higher than true vertical thickness, and they are higher than the actual thickness of the interval. So when we say we wanted to have an isopack map or thickness map, it's based on true vertical, through a stratigraphic thickness of the interval. When we say we wanted to have an isochore map, it means true vertical thickness of the interval. But don't use this one because it is not the actual thickness of the well. Sometimes if you have a, for example, hard copy of a log, you just see this one. You just see this one. And it's very, in the deviated well, it's very hard to correlate the thicknesses of the interval in different parts. So it's better, for example, in a tech log or in a Petrel software, you convert the depth to true vertical thickness or through a stratigraphic thickness, and after that correlate the logs. Okay, so that's a type of thickness map. It shows that, for example, in this part, the geologists pick the thickness of each interval. For example, different well, it has different well. They pick the top and base of the formation and create a thickness map. And for example, in this thickness map, based on this skill or this legend, it shows that we have higher range of thickness in this part. We have lower range of thickness in this area. Okay, that's another type of the map, the 2D map. That's a porosity map. You can see based on porosity or based on the trend of the depositional environment and also log, you can create this type of porosity map. if you want it, before you distribute the properties and create a 3D model of the porosity. You can see, for example, in this part, we have high porosity for this interval. And in this part, you have a high porosity. And in this area, we have low porosity. Also, for this interval, you can see we have high porosity in these areas. Okay, the other maps you can create with a software, or it's better to use actually software because it's very easy. For example, in a petrol software, you can create a deep angle and deep azimuth maps. What is the deep angle? If you have some layers and if imagine that it's a horizontal lines, the slope between the horizontal surface and the direction of the beds is the deep of uh, those interval, and the intersect between this surface, or the direction of this surface that has intersect with this horizontal line is the strike of that. So you can create those on those software. Let me show you. For example, you have this structure map. You just with those software, you can easily create a deep azimuth map based on that. Look at this one. We have different direction of the contours. You can see we have also there different direction of azimuth in this part, and also this map shows the deep angle. It means that the warm color shows higher deep angle. So it means that in this part, look at this part, it's similar to a fault or monocline. We have a monocline or fault in this area. You can see we have warmer color in this area. Also, we can see some type of warmer color in this area. So maybe we have another faults in this area. So with this angle and deep azimuth, you can find the azimuth of the interval, or the angle, the deep angle of the on a structure map, and it helps you to find the trace of faults. You can find the deep of the structure maps. Okay, right now, uh, I wanted to talk about the 3D model. At first, what's the 3D model? The 3D model actually help you. That's a geocellular model that you can distribute the properties, and it creates from a stratigraphic framework, a structural model, Fascist model, and you can distribute the properties into the cell or grids. So it better describe or predict the reservoir behavior in the real world. So for creating a strategy, so at first you create a structure maps. After that, you want it and you pick the top formation, create the structure maps, and after that you wanted to actually uh, create a stratigraphic 3D stratigraphic model. So what do you need? At first, you need the horizon. This horizon comes from, let me show you. This horizon comes from maybe seismic data. For example, a geophysicist give you some surfaces, because some surfaces has better resolution. So, for example, they give you the uh, two surface map, one of them for um, one formation, and one of them for example, for the formation at the base. but you have several formation in the middle. So you must calculate those formation. How you calculate those formation and create those, for example, this one comes from seismic data. This surface at the base comes from uh, seismic data, but you must create those formation at the middle, but they don't have high resolution, or uh, actually you must create those or calculate those. How you can calculate those? Based on top of the formation. You have the top of formation, so you calculate the top of, for example, formation at this one and at this one, and based off the trend of this interval or formation, you can calculate those. Imagine that this is the 3D stratigraphic framework of a formation. So you have this formation, the top based on the seismic data, and you have this base based on seismic data. You can calculate other surfaces based on those. Okay, you can also use, if you don't use the isocore or isopack map, maybe uh, in the well section you don't have any intersect between the layers or formation, but in some part you have intersect because the software just extrapolate the calculated surfaces. So it's better to have isocore or isopack map to create a better uh, calculated surfaces for you. Okay, after you create a stratigraphic framework, you must actually insert or import the faults. Faults as sticks, faults as surfaces or fault lines. You import those and create the surfaces. Sometimes, in most of the times, the geophysicists give give you the fault line, fault and fault surfaces, and you just import them up, and you will apply them onto the surfaces to see the displacement. But sometimes the fault has intersect with, for example, with well, so you can see them onto the well. For example, if you have two wells near each other, one of them has an intersect with fault, one of them doesn't have intersect, so you can see when you wanted to correlate those logs to each other, you can't correlate because you have displacement of the formation. Sometimes you don't have those interval in one well, so you find out that you have a fault here. For example, imagine that we have one well here and one well here. You expect to see this interval, this blue interval in this area, but when you actually have a well here, but you see, for example, 100 100 meter, you have displacement, so you find out that you have a fault here in this area. So you create a fault line after that in applied to the surface on that area. Okay, so uh, the surfaces or fault lines that comes from seismic data, you imported those into the software and apply them on the surfaces, and you see the displacement of those fault on the surfaces. So this fault maybe reduce the volume, maybe sometimes increase the volume of the uh, reservoir or the formations. And you apply them onto the formation that affected by faults. For example, if you have three, four intervals, you apply them and also find out the uh, actually create those framework for all of them. After that, you must create grids. You have just up to now, you have just have a stratigraphic framework or a structural framework of the reservoir, but you must create grids. Why you should have grids? Because you wanted to distribute the properties. Each grid get just one sample or one data point in the vertical direction or in the horizontal direction. So you have the property for several wells, or imagine that you have just the wells for 10 wells, 100 wells. So, but for the location between them, you don't have any data. So you must distribute the properties. Because of that, you must create a grids, and each cell must assign for each cell. You should assign just one value, for example, one value of porosity or permeability or etc. So what is pillar gridding? The pillar gridding is making a skeleton framework. And this skeleton has three components. One of them is the top, one of them is the mid, and one of them is the base. And you, in the pillar grading process, you create a grids. Let me show you in this section. For example, you have a top formation here and base is here. You can create actually some mesh, some grids, and you can actually look at this one. You can have a higher grid dimension or lower grid dimension. For geologists, is as a geologist, is better to have a finer range. But for reservoir engineer, they coarsen these grids because actually most of the time they like to work with grids less than 3 millions because of the processing times. So, but in the petrol, um, you don't have this limitation. You can have about 10 million cells for a formation. But after that, you must coarsen those grids. At first, you create a very fine grid. After that, you distribute the properties, but after that, you can coarsen those grids. After that, after this process, you must divide the zones or the formation in interval into the layers. Why it's is why this part is important for us? Because if you look at this one, this is a log of porosity. For example, we have 10% porosity here, 12% here, 9% here. You must divide this interval into the layers because you wanted to assign one value to each cell. So you divide this interval into a different number of layers and assign a number based on averaging method. So uh, if, for example, if you don't have any layering, for example, look at this, if we have just one layer, it just average, the software just average those interval and give you one number. But if you have different layers, it average each layer and assign one value to each cell. Okay, after that, we have Fascist modeling. Fascist modeling is very important for us because as I told you that in the conceptual modeling part, it gives you a trend. Actually, fascist modeling is not important. It is not an output for this software. It just gives you a trend of, for example, a channel system. It gives you a direction of the different depositional system, and it helps the porosity model to better trend the porosity. After that, you actually you must have a data analysis and uh, do the data analysis to find out the variability of the um, trends. For example, look at this channel system. In this part, you have channel system. Also, in this part, you have channel system. But if you go toward the edge of the channel system, in this part, you have shale. In this part, you have shale. So the variability in this part is very high. The variability in this direction is low. So the range of variability from this part to this part is higher. You can see in this part that uh, the characteristic of this, for example, sandstone in the channel system in this part is very similar to this part, but the characteristic of this sandstone here is different with this sandstone in this part. So it uh, actually it gives us the major and minor ranges. So that's this direction is the direction of major. This direction is the direction of minor. That's very important for us to actually find the variograms or variability in the reservoir. So for a stochastic simulation, you need these variograms. Variograms actually showed you the variability or similarity of the deposit in three different directions. One of them is major, one of them is minor, they are in horizontal section, and one of them in vertical direction. Vertical direction is variability in a well. For example, you have, let's look at again in this well, you have a density porosity, for example, log. It shows you the variability in this direction. So that's a vertical direction. But uh, for other major minor, it shows you the variability. If you have a channel system here, it shows you the variability. The major shows the variability in this direction, and minor shows the variability in this direction. So always the variability in the range of the variability in the minor direction is lower than. Look at this one. If you look at the variability in a minor direction, because we have channel system, and beside of that we have shale system, so variability is high, but the range is low. Why? Because the distance of the variability is very low. But in the major direction, the variability, the range is very higher. Okay, after that, you must create some variograms in different direction in I, J, and K direction. And after that, fit the experimental variograms. You can do that with, for example, Petrol software or RMS software and find those. And using those for a stochastical simulation algorithm. Okay, sometimes you can see this type of variograms. In the 3D modeling, you must create this type of variogram. Uh, I can see again my, oh, okay, right now I can see my cursor. Let me change it to laser. Okay, okay, if you see, what is the variance? Variance shows the degree of dissimilarity between points. And seal, let me show you, I have a better picture, I think so. Okay, I think I deleted that one. But if you look at this picture, we have some data points. We have some data points up to here, and after that it flats. Up to here, it shows that we have similarity between the data points. But after that, we in this part we don't have any similarity. It means that in the channel system, if we see similarity, it increases the ranges, increases this. If we see more similarity, it increases the ranges. And after that, this range is very important for you. And also in minor direction, you can see the distance of the similarity is low because we have channel system here, but we have a shell in this part. So similarity is low. So the range should be very lower. So always the minor range is less than the major range. So, and we will find out that in the also we will find out that ranges in the vertical section. So how it calculated, that's the formula for or equation for finding those points. For example, in this equation, n is the number of data points. For example, here you have 8 data points, and that's a sigma. So that's a phi. For example, you have phi in this part is 3. So you in this part is 5. So you said that 5 minus for lag 1 is 5 minus 3 power 2. For this lag is phi is 7. It means that this part is 7 minus 5 power 2. And after that, software calculate this type of variograms, but you should actually fit a variogram on that data points in 3 direction and find those direction and calculate the ranges. After that, you use those ranges. Finally, the target is you wanted to see in which part the lithology and characteristic of the lithology is similar. For example, in 100, you say that in 100 meter, I have a sandstone with with a trend or very similar characteristic. That's your, for example, major trend. In 20 meter, we have similarity in minor direction. That's your minor direction, and etc. And software uses those ranges to create actually to distribute the properties and give you the trends. Okay, we have 2 types of modeling. One of them is stochastic simulation, and one of them is deterministic. One of the differences, when you have the high number of wells in an oil field, Imagine that you have a high number of wells in a oil field, and you you can estimate that. You can estimate that by the real data, because you have so many data in a field. So you can create a very smooth map that shows you, for example, the trend of the porosity and permeability. Look at this map that's created by deterministic. But if you have a lower number of wells and use the deterministic, because you are not sure that what's the property between them, but it creates very smooth map for you. So if you look at this one, this curve, the blue curve shows you the reality, but the actually the curve that created by deterministic, it's not similar to this blue curve, and sometimes it overestimates, sometimes it underestimates. For example, you see some shale interval in this well, some shale interval in this way. It creates a smooth porosity based on those uh, data points, and it underestimate the porosity because it connected those shales very smoothly to each other, and it underestimated. But imagine that you have sandstone here and sandstone here. It actually create a very smooth contour around those, that we have sandstone in this part, but the reality is not look like this. So it overestimate the porosity. But for a stochastic, it honors the wells, it honors the histogram, it honors the variogram, it honors the variability between data point, and based on different realizations, it gives you a better result. You can see that in, for example, this green part is much better than this red one, but it doesn't give you just one result. It gives you different result. After that, you can go with uncertainty analysis and have a better output. Okay, the last part is volumetric. Our target is to calculate the volume of the reservoir, oil in place, volume of the, for example, net part of the reservoir. If you look at this actually cross section of this anticline, that's the oil water contact, and that's the gas oil contact. So you can see in this well we have just gas, in this well we have just oil, and in this well we have salt water. So based on those, or some of the pressure test result, you can calculate the oil water contact, gas oil contact. So based on those, you can calculate the volume of the reservoir. If you look at this, again, that's the equation we're calculating. You have the area. What is the area? That's your structure map. You have the H, that's the thickness of the reservoir. Maybe that's a net pay. You can apply a cutoff, or net to gross. You can find out the thickness. You have the phi. What is the phi? You have the porosity model. You have the SW, that's the water saturation, that petrophysicist gives you this number, or give you some logs you can distribute as porosity into the model, and you have PO that comes from the or oil formation volume factor. That reservoir engineer gives you that one, and you can easily, after these processes, you can calculate the volume. So just for at the end of this presentation, I wanted to show the result of the petrol. For example, in the petrol, you have this one. The net, the volume net is the bulk volume times net to gross. It shows that how much net thickness you have. For example, you can create a cutoff for porosity, 10% cutoff, 12% cutoff. And after that, apply that onto the porosity, or you have the bulk volume based on the structure maps. So if you times that one to the net to gross, it gives you the net volume of the reservoir. You have the pore, that means pore volume. If you that's a net volume. This one, the result of net times porosity, hydrocarbon pore volume plus times oil saturation, and that one that's one the pore volume of the gas, and also the initial oiling place. And if you give, for example, in the petrol, gives numbers to important numbers as oil water contact, gas oil contact, or create, sometimes you don't have the numbers. Sometimes you have a deviated oil water contact. You can also import them as a surface and calculate those. And in this part, you import the water saturation as a number or water saturation as a model into the petrol. BORS, that's the ratio between the volume of gas to volume of the oil, and also that's a net to gross, and also phi, that's your porosity model. With those models, you can actually calculate the volume of the reservoir. Okay, that's all of my slide. I am open for question. Just in this presentation, I RMS in 2 weeks, 3 weeks, 1 month, if you join a training course. But the reality is the concept behind this reservoir modeling software. I think if you wanted to be a professional geomodeler, you should learn. You should learn some other aspects. For example, what is the conceptual model? What is the diagenetic processes? What is the sequence stratigraphy? What is the different type of porosity, permeability, and etc. And after that, you can easily find out how to work with software and calculate the oil volume or calculate the volume of the reservoir. Okay, that's the end of my slide, and I am open for questions.
Thank you, sir, and thank you, participant, for joining with us in this wonderful session. Hope you have learned a lot from this wonderful workshop. And if you have any question, you can feel free to ask. Okay, one question, sir. Can you please suggest some good books to learn geostatics?
Just for a static modeling, or for other aspects? I think there is one book published by AAPG publication. I will send you the name of that book, but as I said, that you must at least be familiar with other aspects. For example, sequence stratigraphy, for example, like petrophysics, and
No,
other
sir. He means
aspects. Yeah.
geostatistics, sir.
Uh-huh. Yeah, yeah. Yeah, I know several books. Yeah, and I can share them with you.
Sure, sir. I will share with the
Yeah,
Mohammed.
yeah.
You will. Okay. One question I'm getting, sir. Could you, okay, in doing donation using will logs, can I use geological time scale?
Uh, Actually, you mean instead of, let me see again the question, how I can see the
Sir, yeah,
chat.
question is, sir, in doing donation using will logs, can I use geological time scale?
Yeah, for the zonation, sometimes you can use the time scales, but you know that the time scales, that's just based on the biostratigraphy. But sometimes you don't have. For example, imagine that you're working on sandstone, and in very small packages, I showed you some stacking patterns. Most of the time, you don't have any data for example, biostratigraphy. For the sequences, for the large sequences, yes, you can do that. You can use those top of the formation, for example, and some of the time scales. But for smaller packages, you can't use those because those packages are very small. You can find those in the time scales because we don't have any fossils, right?
Yes, sir. So one question more. So what is the difference between variance and semi-variance?
That's a good